Hi all, and thanks for joining this webinar. My name is Christoph Hahn, and with me is Manuel Fedu, who will cover the workflow demos using Speedgoat test systems. Today, we will show you how to test controllers of microgrids and renewables, and also their safety devices. Traditional electricity has been generated in centralized large-scale power stations and delivered via transmission and distribution networks. Today, with the trend towards zero carbon dioxide emissions, renewable energy is on track to soon become the world's largest electricity source. Businesses, communities, and even individual homes are transitioning towards renewables. Advancements in battery storage and electric vehicles even support that trend. According to the International Energy Agency, solar and wind energy combined will soon surpass coal as the largest source of electricity. Additional to the rise of renewables, new technologies like wide bandgap semiconductors enable more efficient and lighter power converters. And here are some resulting technical challenges. Grid-connected inverters and their controllers need to be validated safely and efficiently. High-efficiency converters based on the latest semiconductor technology need to be developed swiftly. And all in all, model-based development and requirements-based testing must go hand in hand within a single end-to-end workflow. So let's now look into how distributed energy generation or microgrids impact the overall power grid. Distributed energy resources can destabilize the grid. More grid-scale energy storage is needed to balance that effect, to balance the variable output from renewable sources. For example, EVs provide back energy to the grid after they have been fully charged. In all cases, ensuring grid safety and stability requires testing methods to validate controllers in advance. So that brings some challenges. Let's look into that together. Well, novel energy management algorithms are needed. The same holds true for algorithms of the controllers. Then the controllers need to interface with each other using protocols like IEC 61850. And to model that, accurate multiphysics models are needed for testing. Last but not least, a high degree of automation is required to test efficiently. MathWorks and Speedgoat provide solutions to all those technical challenges when you develop renewables and microgrid controllers. You can benefit from a fully Simulink integrated solution that provides flexible and automated workflows. It provides a powerful digital twin software and it provides hardware emulation solutions. And it brings modular hardware-in-the-loop test tracks that can scale with your needs into the mix. So before we dive deeper into the solutions and go into the details of the webinar, let's review the agenda together. First, I will motivate why hardware-in-the-loop testing, or HIL testing in short, is key. Then I'll introduce our solution's key capabilities and workflows. Then I will transition to Manuel and he will present specific testing use cases with Simulink hands-on demos leveraging Speedgoat test systems. The first example will be a microgrid energy management system. The second example will be solar inverters, but we'll have a look at different topologies. And last but not least, we'll look at a grid protection device and how to integrate and test that. Last but not least, we'll share the key takeaways with you, followed by the questions and answers session. So, why should you use HIL testing to develop controllers for microgrids and renewables? Let's say you're designing a controller that will integrate into a microgrid. Here are some reasons why HIL testing with a digital twin of the grid running on a Speedgoat test system is beneficial. Well, you need to safely evaluate new controls without jeopardizing the utility grid or risking expensive electrical equipment. You need to de-risk testing further by using all actual interfaces of your converter or controller. You can automate testing to validate your controller firmware for all operating conditions, even faulty ones. You can use Simulink as a single development and testing platform. You avoid translating your code between different environments. And finally, you can test, verify, and validate as soon as possible without having to wait for your final hardware, and especially without needing to reproduce extreme fault conditions with your hardware. So Hill testing can support you by providing a digital twin of your real plant. Hill testing can be especially useful for microgrids with various types of power generation sources and components. It could be running a standalone or island mode, or it could be connected to the grid. Therefore, it's super important to comply with grid codes to ensure a safe and smooth transition. Microgrid behavior can be complex, but thorough understanding and sufficient testing is very important. And model-based design and hardware-in-the-loop testing allow you to test the system in extreme scenarios with different system variations and especially with zero risk. So let me show you a bit more in detail what model-based design and hardware-in-the-loop testing means. First, you can build a model of your microgrid system, usually on the desktop. After you have your model running, you can implement it into a real-time target machine. And we will show you later what to choose and how to do it. Now you have your plant model, which represents your real system. And from the I/O level or communication protocol level, they are running in real time and they behave just like your real plant. The difference is that your plant model is virtual. So when you hook up your controller to the target machine, it's just like you are testing the real system. And you can test them over and over again. And you don't need to be worried about breaking the hardware. So, this was in short the process of building a model for hardware-in-the-loop testing. We call the model which is running in the real-time target machine digital twin. During hardware-in-the-loop testing, you test your controller against your digital twin. Now, let's look closer into three basic components of a Hill test system. First, your system under test. This includes the production controller that requires thorough testing and additional real components like domain controllers, sensors, and actuators. Second, a Hill test bench, including a real-time simulator where you run a digital twin of the plant together with emulated plant components and I/O modules that support data acquisition, signal conditioning, and communication with the system under test. Third, a workstation. You use it to build your simulation models and run application software. It also supports the setup and operation of the Hill test bench. Now, let's dive deeper into the solution's key capabilities and workflows, and afterwards I'll hand over to Manuel for the demos. At the beginning of this webinar, we have identified the key technical challenges from testing controllers for microgrids and renewables. Let's now just go through our capabilities as they address each of these challenges. We want to evaluate early ideas safely without risking damaging the grid. For this, we need accurate simulation models of microgrids and utility grids. Speedgoat test systems can run grid models built in Simulink or Simscape Electrical with hundreds of nodes in a single Hill simulator. For large grid models, you can combine multiple Hill simulators using shared memory links with extremely low latency. You can also deploy multi-physics simulations such as electrochemical batteries, complete wind turbines, even gearboxes and hydraulic systems. Furthermore, when testing low-level controllers, you will need an accurate model of your power electronics topology. Choose from many ready-made topologies optimized for Speedgoat test systems that allow switching frequencies of hundreds of kilohertz, including the switching effects. Among them are AC-DC like NPC or power factor correction converters, or DC-DC like a dual active bridge or a modular multi-level converter with 100 modules or more. With Speedgoat test systems, you can reproduce the actual signal level I/O interfaces of your supervisory controller or low-level controller. Use analog and digital interfaces or sensor emulators. Fault insertion is also essential to guarantee that your controller will behave as expected during cable shortcuts or open circuits. For power interfaces, you can also use our power hardware-in-the-loop interfaces. Another key capability is the protocol support on the signal level. Speedgoat test systems offer turnkey protocol support, including energy protocols like IEC 61850, timing protocols like PTP or IRIC, as well as low-level high-speed protocols like Aurora or SPI. Speedgoat offers test system integration services, including the models and interfaces associated with your specific system under test and project requirements. We conduct factory or site acceptance tests jointly with you and deliver jumpstart trainings, getting you started swiftly. Another key benefit is the Simulink workflow integration. You can automate testing, test 24/7, and connect to all common platforms for continuous integration. And finally, having a single platform helps to simplify development and testing. MathWorks and Speedgoat offer a single platform around Simulink. You can download Hill-ready model examples for your project from the MathWorks and Speedgoat web pages. Let's move on with the demos. For that, I'm handing over to Manuel. Manuel, the stage is yours.
Thanks, Christoph. Now let's illustrate our hill testing solutions for microgrids and renewables with several demos. Starting with the microgrid energy management system. An EMS for microgrids is a control platform designed to optimize the generation, storage, and distribution of energy within a localized grid. In addition, the EMS coordinates connection to the utility grid with the potential for islanding operation when disconnected from it. The EMS coordinates different energy sources such as solar, wind, and conventional generator, and energy storage like batteries in grid energy storage or electric vehicles. The EMS algorithms usually run in a PLC or PAC that contains the suitable processing capacity, I/O, and protocols to handle the optimization and coordination tasks. Hill testing of EMS controller can accelerate deployment and ensure safe operation of the system under all possible fault conditions. Speedgoat test systems can be configured according to your needs and are capable of simulating microgrids, renewables, and utility grids, and providing I/O connectivity to control relays, emulate sensors, or communication protocols. Let's explore a microgrid EMS testing setup in action. The hardware setup for this demo includes a development computer running MATLAB, Simulink, and Simulink Real-Time, which enables instrumentation and real-time testing of our Hill application. We're using a performance real-time target machine to run the Hill simulation of the microgrid plant. One of the test system's onboard Ethernet ports is configured to enable Profinet fieldbus communication. With the device test, which is Siemens PLC acting as energy management system and running peak shaving controls. First, let's look at the model. The model is built with Simulink and Semscape Electrical. In this model, the microgrid is connected to the main grid. In the microgrid, we have the power generation source, which is a solar panel, the energy storage system, which is the battery, and the feeders. We have a control system, which is what we are going to test today. Before we run Hill simulation, let's run the model in real time in Speedgoat target machine to verify the Simulink real-time workflow and to see if the model can run real-time at desired sampling rate, in this case 50 microseconds. You connect the target and click this Run on Target button. It will build the model and download it to the target and run in real time. Now the model is running in real time. The left chart is the grid and battery power, and the right chart is the current. From the user interface, you can define the maximum total power limit from the grid and battery. When more power is needed above this limit, the battery will make up the deficit. This is called peak shaving. You can also do other testing, like changing the weather condition from the solar panel. You can see that the peak shaving control is working. The battery is doing nothing when the load is low, and besides the solar panel, all the power is from the grid. As the load increases and power reaches the limit, you can see that the battery kicks in, so the power from the grid is flattened. You also see that the results looked very close to the desktop simulation, which is in dot lines, and the computation throughput, task execution time, is within the budget. From this model and the loop testing, we verified this model is real-time capable. Now let's set up the hill and run. This is the hill hardware setup. Let's set up the software now. At software level, we separate the model into controller and plant. For controller, we use Simulink PLC coder to generate structured text file that you can load into the Siemens PLC. The rest of the model, which is the plant, runs in the Speedgoat target machine as the digital twin. When you choose to run hill simulation, the controller block in the model is nothing but I/O interface, and we need to map the interfaces to the device under test in the model. This is the I/O signal mapping and routing on the plant side, using Simulink inputs and outputs and signal packing and unpacking blocks. Since we use a Speedgoat I/O 752 Profinet card, we use the corresponding Speedgoat library blocks to configure this protocol and map the signals. On the PLC side, we also map I/O signals, compile and download the PLC code, and run the PLC. And the PLC control is waiting to be triggered from the plant. Then we run the plant model in the Speedgoat target machine. Now you see that the controller is running, all lights are green, and the plant is also behaving as expected. You can see that the peak shaving is working. Now I can flip the switch to island mode. You see that the power from grid is 0 now, and the battery needs to provide more power. Now let's go back to grid tied mode. And you can see that the power from grid is resumed. You can also ask battery to provide more power, or you can let the battery receive some power. Let's zoom in and see some details during the transition. So that was our first demo. Now let's move on to our next use case, testing embedded controllers for power converters that are connected to the grid. Grid converter controllers strive for higher power efficiency and density and help implementing hybrid systems that can combine solar power generation with energy storage systems. Converter controllers need to integrate advanced control algorithms such as the maximum power point tracking, or MPPT for short, voltage regulation, and grid synchronization, and must achieve regulatory compliance for requirements like low voltage write-through, frequency response, and reactive power control. The grid inverter control algorithms usually run in a microcontroller. Hill testing of a converter controller accelerates deployment and ensures safe operation of the system under all possible fault conditions. Now, simulation fidelity and speed are crucial for inverter hill simulation, so you can leverage a twofold solution to meet diverse requirements. For simulating averaged inverter models that ignore switching effects, and for detailed switching models of inverters running up to 10 kHz, you use a CPU-based workflow. This combines multi-core processors, high-speed configurable I/O modules, and C-code generation capability of Simulink and Simscape Electrical. To actually simulate the fast switching dynamics of high-frequency inverters, use Speedgoat programmable FPGAs, which increase hill simulation bandwidth to the megahertz range. Let's now delve into these solutions. Starting with a CPU-based approach with our next demo. We'll explore switched hill simulation of a 3-phase NPC solar inverter and the testing of the NPC controller switching at 5 kHz. As for the previous demo, the hardware setup includes a development computer, enabling instrumentation and real-time testing, a performance real-time target machine running hill simulation of a grid-connected solar PV system, including an NPC inverter. The device under test is a microcontroller running the inverter control and MPPT algorithm, as well as an oscilloscope to monitor the voltage and current of the grid and the DC bus of the simulated power system. Let's now switch to Simulink and check our HEAL system model. The model is structured around two primary blocks: an instrument panel modeled in Simulink dashboard components to enable real-time interactive testing directly from the Simulink canvas, and the power electronics model, which includes the interface with the inverter controller. The electrical system consists of a 25 kV microgrid connected to a 400 kW solar PV system. It is implemented using the Simscape Electrical Specialized Power Systems library. The grid inverter is a three-phase, three-level NPC switching inverter directly controlled by PWM firing pulses generated by the inverter controller. Hardware interface between the simulated power system and the inverter controller is established using a PWM interface that captures the controller gate switching signals. Additionally, there is a digital to analog interface that outputs the simulated voltage and currents for the power grid and DC bus. These interfaces are enabled through a configurable I/O module configured to use direct memory access, which reduces overall I/O latency and lets us run this application at 40 kHz. Let's kick off our HEAL demo to see how different weather conditions affect the MPPT controller. Here, the predefined weather conditions simulate a typical day from morning to late afternoon, with temperature and irradiance levels rising and then falling. We've been condensing this input profile on a 60-second time window for illustrative purposes. Before starting the simulation, we power up the controller and flash the inverter controls from Simulink using embedded coder. We switch to the HEAL power system model and select the HEAL simulation mode, build and run the application in real time. Now the simulation is operating in closed loop. As the irradiance increases, the solar panel produces more power. The MPPT algorithm continuously tracks the DC bus voltage and the solar panel output, adjusting the DC bus voltage to optimize power output under varying conditions of irradiance and temperature. While the application runs, we can also monitor the control PWM signals issued by the inverter controller with an oscilloscope or use the Simulink data inspector to review additional model data like the captured PWM duty cycles and the phase voltage waveforms of the NPC inverter. In addition to the predefined weather profile, you have the option to manually adjust radiance and temperature. Let's imagine that a thunderstorm hits unexpectedly in the middle of the day, causing a sudden drop in both irradiance and temperature. We see an immediate change in the power output from the solar panels, as well as shifts in the DC bus voltage and current. Next, we'll assess how changes in DC frequency impact the overall stability of the power system. Using the instrument panel, we'll set a 5 Hz frequency variation to occur at 20 seconds, returning to nominal frequency of 50 Hz after 1 second. During this test, you might notice a minor disturbance in voltage and power when the frequency changes. However, the solar system remains synchronized with the grid frequency. For our final test, let's simulate a phase short circuit fault and assess system robustness. To initiate a fault, simply flip the fault switch to the on position. This action will create a 3-phase short circuit fault on the grid side. Let's stop the simulation and check acquired power system data in Simulation Data Inspector. You'll notice the fault lasted only about 1 millisecond. During the fault, the inverter and AC waveforms distort, showing noticeable spikes in bus voltage and current, which is expected. Despite these disturbances, the system recovers quickly once the fault is cleared. Now, to outline the FPGA workflow, let's explore the use case of a 3-phase grid-side converter and the testing of grid forming and grid following controls. Let's assume the converter controller is running at 20 kHz and we want to capture the fast switching dynamics of the grid-side converter. In this case, as I mentioned earlier, FPGA-based simulation is required to achieve microsecond to nanosecond level time steps, high-speed connectivity for fast-speed RAM capture, and accurate emulation of converter phase currents. So, let's move on to a grid-side converter hill demo and dive deeper into the FPGA workflow. We'll be using a similar setup as the NPC inverter demo. This time, the Speedgoat hill test system is equipped with a Simulink programmable FPGA to simulate the grid-side inverter. The microcontroller on the test will be running both grid forming and grid following controls. Let's start by exploring how to create and build an FPGA-based hill simulation model for the grid-side inverter. First, you model the inverted power electronics and interfaces to the power grid. The model can be used for desktop simulations and as a golden reference to validate the next design stages. To generate an FPGA-compatible design, you use the SimScape HDL Workflow Advisor, which essentially converts your SimScape plan model into an HDL-compatible implementation that can be turned into an FPGA application. Next, the Simulink HDL workflow guides you through generating target-optimized HDL code and mapping FPGA interfaces such as channels to capture PWM controller signals and emulate three-phase currents of the inverter. Once the Simulink HDL workflow is complete, you encapsulate your FPGA design in a Simulink library block ready to be integrated into your system-level model for real-time execution. This setup allows for combining FPGA and CPU-based simulations. For instance, we run an aggregated synchronous generator model on the CPU to assess how the power electronics converter affects grid stability. Now we can use this hill simulation to test the grid inverter controller in action. The inverter is set to deliver 0.25 per unit of power to the grid under varying conditions. At 30 seconds, we'll simulate an increase in grid load to see how it affects grid stability. First, we start the simulation with a grid forming controller connected to a grid with a sizable inertia. The results show that the controller successfully maintains the power output at 0.25 per unit. We can also observe the effect of switching dynamics on the grid, particularly the 20 kHz current ripples. As the load increases, the synchronous generator on the grid manages to maintain stability. But what happens if we introduce the converter into a weak grid with less inertia from synchronous generators? In this case, we see the grid frequency drops more significantly and quickly. In a real-world scenario, this could lead to a grid blackout. To counter this, we'll update the controller with a grid-forming algorithm that can provide virtual inertia to the grid. Let's restart the simulation. When the load increases, the updated algorithm helps support the grid by providing inertia and additional power output, resulting in a stable grid. Keep in mind, we may observe some initial noise in the power output due to the grid forming controls. This concludes our demo on grid inverter controller testing. It is time for our last topic, testing of a grid protection relay. Protective relays are integrated throughout the electric network to protect the various zones of the power system, ensuring safe and reliable operation of the overall power grid. Let's explore a protection relay hill setup in action. We are using a smaller scale demo test setup, which integrates a commercial off-the-shelf feeder protection relay, the SEL 751, a performance real-time target machine equipped with an internet-based IC61850 interface, and analog and digital IOs. IOs and power are routed to the protection relay through a dedicated harness inside the cabinet. Let's now switch to Simulink and check our hill system model. The model is structured around two primary components: a SCADA system, designed with Simulink dashboard components to monitor and control the operations of the relay and the power system, and the power grid system model, which includes the interfaces with the protection relay. The power grid consists of a bus feeder operating at 416 kV based on the IEEE 13 node test feeder circuit. It is implemented using SimScape Electrical to study the electromagnetic transient behavior. Communication between the simulated test feeder and the protection relay is established using IEC 61150 Goose messaging blocks, allowing for data acquisition from the protection relay, an analog interface that transmits the simulated power grid three-phase voltages and currents to the relay, and finally a digital interface that provides access to both trip and reclose signals issued by the protection relay. Let's start our hill demo using the SCADA and run the simulation in nominal condition, where no faults are present in the system. Such a stable configuration lets us analyze the power flows at each node and, for instance, inspect if there are any congestions in the feeder lines. Additionally, using the IEC 61150 Goose messaging, we can analyze the current and voltage vectors at the relay's connection point, here represented with the node 692. Data can also be validated in the protection relay display. This SCADA system can also be employed to trigger faults such as overcurrent, overvoltage, or underfrequency. Let's initiate an overcurrent fault and observe the protection relay's response. To begin, we'll open the Simulation Data Inspector and select the electromagnetic transient variables. We can observe that the protection relay successfully activates the trip function right after the overcurrent fault has been triggered. Additionally, the relay required 100 milliseconds to trip and open the breaker, matching our current trip delay configuration. The reclose function then activates after the configured set time of 2.5 seconds, attempting to reclose the breaker 2 times. So the relay correctly isolates the fault and restores the power system to normal operation. So we can say that the protection relay and the Goose messaging operate correctly in an overcurrent scenario. This wraps up our last demo. Christophe, I'll now let you conclude this webinar.
Many thanks, Manuel. So let's wrap up today's webinar. There's a single key takeaway for you today. Speedgoat Test Systems and Simulink provide a testing solution for all aspects of testing controllers for microgrids and renewables. Well, why is that? First, you can create digital twins of your grid or its components covering multiple domains running at the desired frequencies, such as the switching frequencies of your power electronics hardware. You can develop and test in a single and fully integrated environment that fosters agile development and helps you to automate testing. Speedgoat test systems are performant, configured to your needs, and provide all levels of capabilities for your testing needs. Thank you for staying with us until the end of this webinar. You want to learn more about real-time controls testing? Then find additional content linked here.